In Module 6, we talked about the sampling distribution of a sample mean. More specifically, we learned about the central limit theorem that told us that under certain conditions, which generally meant that we needed to have our relatively random and unbiased sample, and if we either knew that we had a normal distribution or our data already looked symmetric and bell-shaped, or if we had a sample of at least 30, then we would be able to say that y bar, which was our sample mean, would be approximately distributed normally with a mean of mu and a standard deviation of sigma over the square root of n. Or written slightly different, we would have mu sub y bar would be our mu, and sigma sub y bar is our sigma over the square root of n. And again, that's just saying the mean of y bar, the standard deviation of y bar. And so we knew we could use this normal distribution, which allows us to use other things that we've learned with the normal distribution. We could calculate our z-score by taking our sample mean minus the mean of y bar, which was mu, divided by the standard deviation of y bar, which was sigma over the square root of n. And we could use that to find probabilities using our table just as before. This was great. So our goal moving forward is to start doing hypothesis tests and confidence intervals for a mean. And generally when we've done hypothesis tests and confidence intervals, we've used a z-score. But there's going to be one little problem that we need to talk about here to understand first why things are going to change a little bit before we dive into how they're going to change. And our problem is this sigma, or the population standard deviation. So first, looking at my z-score up here, notice that sigma is part of that. And so we're talking about why sigma is a problem. So let's think about when we perform a hypothesis test. So when we do perform a hypothesis test, we will have a rough idea for our population mean mu. And that's mainly because when we do a hypothesis test, we have that null hypothesis test. Now, there's also an alternative hypothesis, and so because we have this null, we aren't really sure about it. As we might be testing to see, well, is it bigger than what I thought it was, or was it smaller than I thought it was? So I'm not sure, of course, that the null hypothesis will be true, so my value that I'm going to use for mu, my population mean, I'm not sure about. Okay, now let's think about confidence intervals. So when we construct confidence intervals, we are not going to know mu. Okay, why are we not going to know mu? Well, just as when we were working with a categorical variable, when our goal was to find p, the population proportion, I didn't know that value. I was trying to estimate that value. So we're not going to know mu when we're working with a quantitative variable because we're trying to estimate mu. Now, pausing here for a moment, I said our problem is going to be sigma, the population standard deviation, but up until this point, I've been talking about mu, the population mean. Okay, so really, mu is what leads to our problem with the population standard deviation. So let's think through this. So if we are uncertain about mu, right, which is our mean, that means I'm not going to know sigma, or the population standard deviation. Now, why will I not know sigma, our population standard deviation? Well, keep in mind that standard deviation is a measure of like the typical or the average distance from the mean. So if I don't know what number to put in the middle, that mean, I don't know how far to go out from that value. So it's really that uncertainty in our mean that makes us not know the population standard deviation. So what are we going to do? Right, so what we had is this Z formula. Same one I have above, I'm just copying it down. Let's talk about what we're now going to have. Y bar and mu weren't necessarily our problem here. It's mainly sigma. And instead of sigma, I'm going to put S in there. That's the only thing I'm going to replace. So first, as a reminder, what is S? S is our sample standard deviation. So the one that would actually come from the data we collect versus sigma, that was the population standard deviation. So right now, hopefully it seems like a pretty reasonable replacement, that I'm going to take this population standard deviation that I don't know. I'm going to replace it with a standard deviation that I do know, just my sample one based upon my data. Seems reasonable. However, as soon as I do that, I don't have this Z anymore. I have what's called a T. So that sort of leads us to the question, well, what's T? So let's talk about T next. So we're going to start by looking at a picture of the T distribution. But to understand how it's different, we're going to start with our Z distribution. So Z here I'm going to draw in black. All right, so our Z distribution has a symmetric, bell-shaped looking curve with it. And it was centered at 0. Okay, now we're going to draw T on top of this graph. And so first, as a visual, if you imagine now here your perfect looking Z distribution, imagine that someone came along and sat on that peak a little bit. That's going to be sort of what our T is going to look like. Our T, I'm going to draw here in pink. It's also going to still be centered at 0. It's still going to be symmetric. It's just going to be a little bit thicker in this tail area. So that's why it's higher here. So still centered at 0. Peak comes down a little bit. So let's talk about how these are similar and how these are different. All right, so first, T is symmetric and unimodal. Or again, kind of what you would think of as normal looking. Just like Z. So the shape of the T looks a lot like the shape of the Z. T is centered at 0. Just like Z. So how is T different? T will have a larger spread than Z does. And more specifically, T's spread changes based upon this new thing we're going to talk about, which is called degrees of freedom. Which you'll see labeled as DF a lot. And how degrees of freedom is sort of calculated is it's based upon our sample size. All right, so hopefully let's talk about why T's spread changing might happen and sort of why sample size plays a role. So going back and looking at my formula I have down here, Z and T look a lot alike. I'm taking this population standard deviation and replacing it with a sample standard deviation. And again, hopefully that seems like a pretty reasonable thing to do. But as soon as I'm talking about a sample standard deviation, a number calculated from my data, how big that sample is sort of matters to me. If I have a data set with only 3 observations in it, I can calculate a sample standard deviation for that. And I don't know how much I'm going to trust that number because it's based on only 3 observations. Versus if my sample size, I sampled 100 people and I calculate the standard deviation, I'm probably going to trust that number quite a bit more. So when we think about this degrees of freedom and how it's going to change our spread, the larger our sample size, the more trust I feel like I can put in this sample standard deviation. Versus the smaller the sample size, sort of the less trust I'm putting in the sample standard deviation. So that's the idea of the T distribution. Now when we actually start talking about hypothesis tests and confidence intervals, you're going to start seeing T pop up. So kind of to end this video, so why are we even using this T? We don't know sigma. And we're going to be using S, our sample standard deviation. That's our reasoning as we dive into doing our hypothesis test in the next video.